I'm super excited for this party. No music?
We got you. Introducing Spinphony. I'm Gene,
And we are Ibrahim.
All you gotta do is press play. You got music. Let me show you what's going on under the hood. So what our computer is doing right now is we're doing a short-term Fourier transform. So essentially we sample audio at 8.4 kilohertz. And so as these samples are coming in, we wait until we have the number of samples for our window, which in our case is 2048. So once we have 2048 audio samples, we're gonna take this window and we're gonna do a DFT on it. So if you remember how DFT works, since we have 2048 inputs, we're going to get 2048 outputs or frequency bins. Our first idea was that if we want to get 4 frequencies, we should just take the ones that have the highest amplitude. But the issue with that is, for example, if I'm hearing a C, we're going to get a high amplitude for that C at our fundamental frequency, but we're also going to get high amplitudes for our harmonics. For here you can see the first harmonic and the second harmonic. Now, an additional problem is spectral leakage. If we have a high amplitude at C, we're also going to get a high amplitude around C. This is called spectral leakage because of the number of bins. So we don't want the frequencies around C to be ones that our other motors are playing. So our solution is a saliency score. Instead of taking all 2048 frequencies, we only take 60, which are associated with notes from C2 to C7, so it's around 5 octaves. And so if we hear a C, we're going to take our fundamental amplitude and we're going to add it with the amplitudes of all of the harmonics, C3, 4, 5, 6, and 7. But when we do that sum, we weigh it. So our fundamental frequency will be weighed a lot more than our harmonics. And so after that, we do that for each note, and then we take the top 4.
And that's exactly what we can see here. So this is our real-time Fourier analysis. You can see the input audio, which we play here, in real time, and you can see our Fourier reconstruction with exactly 4 frequencies, and that gives you our music when it signals or when it's sent to our motors.
And the way it's being sent is by UART. So the way UART normally works is that you have a CPU interrupt. But the problem with that is when you interrupt the motors while they're playing, you have breaks in the audio. So the way we solve that is with direct memory access. What this does is the laptop serial sends bytes into a buffer, which is stored without interrupting the CPU. And we have a main loop, which is simply reading from that buffer into a streaming buffer. And in this process, it actually converts these numbers into phase increments. Phase increments are applied to the motors each tick. And these ticks happen through the motor pit timer at 20 kilohertz. So every 1 over 20 kilohertz, the main loop is interrupted, and then we read from this streaming buffer a phase increment. We add that to each of the motors, and then if the phase overflows, then we say that we've moved 1 tick. So that's how we interrupt the main loop, and then we read from the streaming buffer. So that's how music is being played over here.
Well, let's take a closer look at the hardware here. So obviously we have 4 NEMA 17 motors, and if we look at this enclosure, we have 4 chambers here that are sort of amplifying the noise, because if I were to just hold these motors while they're playing instead of screwing them into this enclosure, you wouldn't be able to hear anything because they require mechanical resonance to actually produce the noise. So down here is just a box for all of our electronics, and it fits snug right below our motors.